So, no? Yeah, I say no. It's not working? Can you hear? Is it working? Yes, make sure the microphone is working first. So, ah, so maybe just closer. Yeah, okay. How's that? Is that better? Okay. The videographer says we're good. So, okay. Well, let's jump in. This is the first lecture. Um, I'd like for you to know that the first lecture and the last lecture are actually more general than specific to directed energy deposition. So I warn you in advance, and I think it's important to lay the groundwork for the place of directed energy deposition in additive manufacturing. So I want to talk some about the development of additive manufacturing. I want to talk some about really what the status is today. And this provides basically the groundwork on which directed energy deposition is built. So we can define additive manufacturing according to ISO ASTM 52900. This is a standard that is effectively the dictionary of additive manufacturing. It's all the terms and the definitions of terms as they relate to additive. And I'm happy to be one of about 10 people that actually sits on the committee and actually develops the terms. So I've done this for the last 15 years or so. So anyway, here's additive manufacturing. It's a process of joining materials to make parts or objects from 3D model data, usually layer upon layer as opposed to subtractive manufacturing and formative manufacturing methodologies. So this is where we are today with the technology. I'll talk a little bit about how we came to call the field additive manufacturing before this lecture is over. So there's a historical perspective that comes from an article that I wrote with Joe Beeman and Terry Wohlers, which introduces volume 24 of the ASM handbook series on additive manufacturing. It's a very nice volume, and we sort of talk about how it all came to be. And the main thing to appreciate is that there were really sort of three eras of additive manufacturing. The first is what I call the additive manufacturing prehistory. This is people who did additive manufacturing but without a computer. And we'll look at some of these processes. It dates back, I've gone back primarily in the patent literature in the United States, but really also a few other places. It goes back, the earliest I've seen is 1860. And it goes all the way up through about 1960 because what you have to appreciate. Well, I'll save my comment for the next part here. The second part is of the three is what I call precursor additive manufacturing processes. These are technologies where the inventor knew how to use a computer and could use that to drive a machine, an additive manufacturing machine. Those of you with experience with additive know that the computer is pretty important. You can't really do additive manufacturing without the computer, and it can't be a large mainframe computer. It has to be a distributed computer, a desktop. And so we really can't have additive manufacturing before desktop computers were available. And from 1968 to 1984, desktop computers were available, and researchers were using them to invent and develop additive manufacturing processes, but they had no customer because nobody had a computer. In this period, you have to appreciate that it's before Apple Macintosh came out with its intuitive point and click technology, and the PCs that were available, primarily IBM and others, and in this time period they were available, but they all operated MS-DOS. It was before Windows. So if you've worked in DOS before, you can appreciate why just an average person, living their life would not find it particularly attractive. It's a very difficult program language to use or system to use. The third area is what I call modern additive manufacturing. Again, from about 1984. 1984 is when the Apple Macintosh came out. And over the course of about 3 years, it was unbelievably rapid how the computer came from being really something nobody knew about to something that everyone owned at least one of. It was an incredible rapid period of transition to the computer. So now, once everyone knows how to use a computer, it's relatively easy to market a product like a directed energy deposition fabricator that uses a computer, because everyone knows how the computer works. Before that, the computer was almost like a scientific piece of equipment to researchers, like an oscilloscope or an electron microscope. They knew how to use it, but no one else did. Okay, so this is it's a very fine table here showing the three areas in terms of the patent literature. So these are the patents that have been issued. And up here at the top are three legs of additive manufacturing in the prehistory. So this is before there was a computer, but people were still doing layered manufacturing of parts. And there are three areas. One is topography, which deals with geographic land masses. And you see there are a number of patents. Perhaps you can't read them, but at least you can appreciate there are 8 or 9 patents in this period that deal with this. There's a couple in material deposition, which is important for this course because both of them would be classified today as directed energy deposition processes. And we'll look at those in a minute. Then the third one is photosculpture, using photographic techniques to build three-dimensional objects. So that's the first area. The second area is the precursors, and I find it really interesting here because most of the processes today, when we credit the inventors of the process, it's really not the first people to have developed it, because when we get down to the modern additive manufacturing processes, down in this row, let's get past that. Yeah, here. When you get to the additive manufacturing processes, this is where all the familiar inventor names are. Chuck Hull for vat polymerization or stereolithography. Carl Deckard, who came from my place to do powder bed fusion, laser sintering. They're all down here in this modern era. But in almost every case, you can find someone up here that invented the process first. But they're lost in they're forgotten memories, largely. And the reason why is because they developed the process, but there was no yeah. Oh, thank you. Yeah. From, let's see if I can get the pointer work. Here we are. Yeah. You see that okay? See the pointer? Yes. Yeah. Yes, from about 1988 or so through to about 2000. We'll see this in a later slide. But from basically the decade of the 1990s is where virtually all of the additive manufacturing processes we know today were invented. There are 7 classes of additive manufacturing process. All 7 were invented in the period from about 1987 or 1988 to the year 2000, 2001. Okay, let me charge ahead here. Let's look at some of the prehistory. Let's look at some of these. This is a figure from a prehistory patent. This is Blanford's patent. It was issued in 1892. And what it shows this topograph, and what Blanford proposed to do is he would take an aerial photograph and create the topograph. Then he would cut by hand along the top of the lines of constant elevation, and then he could use that to create a die set like this by separating the plates and stacking them. Again, and then he used this actually as a mold to create paper replicas of the elevations, a three-dimensional map, as it were. So this again, we would call this today, it would be sheet lamination technologies, right? But in 1892, here's an example of modern one. This is M-Course machine. They're an Irish company. I think they've gone out of business, but they used just laser printing paper as their feedstock and glued it together, and then came in with a cutter to cut the parts out. This is I think my favorite of the precursors. This is Baker's patent. It was issued in 1925, and so we celebrate its 100th anniversary this year. But the Baker patent is basically what we would call directed energy deposition today. What it shows is, you see, he's using a moving weld head to create parts. I guess this would be maybe I suppose it would be the electric arc technique that we use today. But you can see he has the base plate. He builds the part by moving the weld head around. And it's called a method for creating decorative articles. Again, it issued 1925. And I sort of enjoy the fact that they even show a little crack here, right, in his drawing. So so he was completely truthful, I think, in terms of his technology. Yeah, and of course we know this. This is what it looks like today with directed energy deposition. The third area was photo sculpture. I used Francois Willemey's photo sculpting lab in Paris in the 1870s. And what he did is he developed a method for using this sort of linkage contraption to take a silhouette photograph and to turn it into a wedge of a three-dimensional object. So you see his sculptures here, the sculptures, these are all made from photographs. And the way his studio worked, this shows a subject sitting on a platform that's split into, I think, 24 different wedges. And then you see these two windows here. Behind each window was a camera. And so the photographs were taken 360 degrees. And then from the silhouettes of those photos, he was able to create a three-dimensional object. Basically, 1/24 of a wedge of whatever the object was. So this shows a somewhat dated photofly from Autodesk. So there are much better techniques now for doing this. But basically, it's a way to take. This uses, I think, just iPhones. It was an iPhone app. And so you could just basically walk around and take photographs of the subject, and then it would turn it into a point cloud that we could then develop to send to a printer to print. I showed this. This is an example of that, a personal example. This was, let's see, where's Manjaya? Is he here or out somewhere? Oh, there, yeah. He spent time in Paris at the École, and this was the conference that was at that same university about, I don't think it has today, but it was about 15, I guess maybe 20 years ago now. But what happened at the meeting is someone came up to me and said, here, let me scan you. And they just simply held a scanner around like this. And then they said, come back tomorrow, we'll have something for you. And so what they had was this disc. It's about maybe 10 or 12 centimeters in diameter, sitting on a titanium plate platform that they printed earlier. And so within a day, they were able to process the image into a nice medallion. It had, it had the Eiffel Tower and some nice French words on the back of it. And they printed this thing out overnight, I guess, and then had it for me. So again, there's plenty of opportunity even today to use photo sculpture. Okay, let's check in. Let's look at some precursor processes. These are people that invented the technology, but it didn't go anywhere. I showed this. This is Swainson's patent from 1968, and it was never commercialized because it was a 3D copy. And so what he did is he had a subject here. He used laser interferometers to capture the geometry. It was sent then over here to cross the laser that would build the part. Well, this technology worked fine. This technology was never reduced to practice. But the reason I show it is not because it's of the early state here, but rather because it's the first patent that I found with additive manufacturing where you see a computer here. This was 1968. So this was a DOS type computer that shows here again the first place where we see this. So I consider this to be pivotal in terms of moving from these precursors into the from moving from prehistory into the precursors, because now we have a computer to drive the process, even though nobody knew how to use it. Here's the precursor patent. This is Sirod. He was a French person. I'm not sure why the Frenchman tried to get a German patent, but he did. And this is from his German patent application. It was 1972. And what it is, it's basically directed energy deposition with a powder spray. So we see, the welding source. These are two weld heads. Here's the part being, the powder is falling down from a hopper, so it's not very directed. It's sort of a cloud of powder. And but it's complete to be able to build the part, and it even has a recycling apparatus on it. So this is, I think, the first case of directed energy deposition in the precursor mode. So we jump from Baker's 1925 patent, where there's no computer, to this patent where there is a computer, and then we jump, of course, to the modern technologies later. I can skip past this one. This is Ross Householder's patent on laser sintering. Again, 1979. It was 8 years before Carl Deckard's patent that we know about. Kodama in Japan. Many Japanese claim that additive manufacturing was invented and began in Japan, and they do that on the strength of this article that was published by Kodama. I forget, he was at a research institute outside Tokyo. But it's back polymerization. It's stereolithography. He has sort of the window on top, which would be like our the micromirror array approaches. He has a window on bottom, and the part's pulled up. This is like carbon 3D split technology today. And then he also, of course, has the gantry approach with a point source, which is the way most stereolithography is done today. All done in 1981, but it did not go anywhere. This is Herbert's. Herbert was an American at 3M Technology, and he also in 1982 invented stereolithography. This is his apparatus. Again, we see the computer and an HP plotter to create parts. Both of these technologies were years before Chuck Hull started 3D Systems, which is the person that we credit with the invention of laser stereolithography. Here's a photograph of Chuck in front of his machine. It also shows the SLA-1, what I consider to be the first modern additive manufacturing machine. Came out in 1987, only 3 years after desktop computers became available. 3 years he went to. So this is a guy who was in the right place at the right time, and was the first one out the door with the machine. This shows some of the early articles. I thought those were kind of interesting. Here's Herbert's 3M's part, stereolithography. Kodama's part from 1981, stereolithography. Ross Householder, 79, his first article, which is sort of a sand binder material, sort of a casting core type material, 1979. Carl Deckard at our place, this is it's not nylon, it's polypropylene, I think is what he used first in 1986. And I also show my 1990 part. This is the first metal part that was ever produced on a modern additive manufacturing machine. And we did it in our lab in 1990. It was on the heels of the first materials patent in additive manufacturing, which I worked on the multiple materials system patent that also issued in 1990. Okay, so here's all the inventors This is not the date of the patent, this is the date of commercialization. This is when the process, quote, hit the market. And what we see is that, again, if you look at this, from 87 to about 2001, all of the processes were invented and commercialized in that period. It was a very exciting period to be alive in the world of additive manufacturing. But anyway, we see who the credited inventors are. In most every case, there's someone behind it, at least one person, who invented the process in the precursor phase. But again, they're sort of forgotten in history. I think you have copies of these, I think, so I don't think I need to go slow. Right? We can look. Yeah, if you want to go back. Moving sort of a little bit towards the modernity, what's going on now. One of the big historical events was the formation of ASTM F42. It's an additive manufacturing standards development committee, and they have 78 standards that was formed in 2009. So it's been about 15 years now. We have 65 items in the works. The next meeting, I mean, everyone's invited. It's an open meeting. It's going to be in September in Manila. I will be there. So maybe I hope you can welcome you there as well. I give the URL for the website so you can see what's going on. One of the important aspects of F42 is we credit this committee with actually coming up with the name additive manufacturing. So we'll talk about that in a minute. On the heels of F42 was the ISO Technical Committee, TC261, which is the ISO equivalent committee. One of the things that was very important in the development of additive manufacturing standards was this collaborative agreement that we started talking about in 2011, right after TC261 was formed, but it was not really formally approved until 2016. And what it is it was a collaborative agreement. So ISO and ASTM agreed that they would work together to produce standards. It's like, I mean, it's almost unbelievable to think of this. It's like Coca-Cola and Pepsi deciding that they wanted to produce a cola product together. I mean, who would think to do this? Because these are competitors, ISO and ASTM. And the reason why we push this through is because what you don't see on this slide is that the TC261 committee members were all the same people as the ASTM F42 committee. We were all coming to the same meeting. We were all working together. We were all collaborators. And by doing this joint agreement to develop standards together was, in my opinion, was an incredible accomplishment. Because what it allowed, the way things normally are done, if you've ever worked with standards, is ISO goes off and creates their standard. Let's say it's going to be on directed energy deposition of titanium. And then ASTM goes off over here. They develop their standard on directed energy deposition of titanium. But obviously, they work separate from each other, so they're different. And so what happens is, you know, you and I, who are the customer, first of all, we have to figure out, well, who do we believe here, right? And so becomes pressure to try to, it's like, come on, guys, let's just have one standard. So what follows then is a very painful process of taking these two standards and trying to reconcile them into a single standard that happens after the fact. It's very painful, and it makes the two sides kind of enemies, right? Because ASTM says, well, we don't want to change our standard, and ISO says, well, we don't want to change ours either, so we have to fight with each other to make it happen. Well, imagine this much better approach that we did here, where we basically said, look, we're not, when it comes, if ISO wants to do a directed energy deposition of titanium standard, what they do is they come to ASTM and say, hey, you want to develop a joint standard together? And ASTM says, yes, let's do it. And what we form is we form a joint committee of all the interested people on both sides who want to develop that standard, and they write only one standard from the beginning. And they don't do it as enemies, they do it as friends, right? Because they're working together and collaborating, and everyone's hearing, you know, it's just a much different dynamic. And so everyone's happy. We get the single standard out, and we don't have to worry about having to reconcile. Anyway, that's a long-winded explanation of this very important aspects of standards development. Additive manufacturing was the first technology to do this. Of all the technologies that ASTM and ISO have done, which are thousands. So I'm very proud of that. So we're working to produce standards together. What happened then very quickly after that is other standards development organizations said, we want to write standards too. So what we've done now is we actually, in 2016, we formed a thing called the AM Standards Collaborative. And what it is basically it's anybody that wants to write standards in additive manufacturing. If you want to try and coordinate the development together, you're welcome as a volunteer to join this group. There's 21 standards development organizations now that are members of the Standards Collaborative. And I'll talk a little bit more about it later. But anyway, you see some of the organizations down here that are developing standards. Again, trying to coordinate the development.
Why Manila?
Yeah, sorry?
Why Manila?
We just move around. The question was why Manila. Yeah, we have 2 meetings a year. Both meetings are ISO and ASTM, TC261 and F42. And we meet always in the spring in the United States somewhere. The last one was at Texas A&M this spring in Texas. And then the other one is somewhere in the world. And it just happens to be the Philippines this year. So, yeah, so it'll be, I don't know where it will be next year. I don't remember the schedule, but anyway. Yeah, I think it was in the UK last year. Right. So anyway, the deal was, I showed this slide, before 2009, if you went to the literature, you would see all kinds of names for this technology. And I show you just some of the more popular ones here. There were a dozen names for this technology. And depending on who you were, you would sort of champion one of these. But you know, nobody, there's no uniformity whatsoever. So imagine with this scenario, with this foundation, coming together as a standards development committee for the first time. This was in January of 2009, when about 100 people met in Pennsylvania to talk about trying to form standards in additive manufacturing. So we approved that, but everyone was very excited in the meeting. I was actually, I was at the meeting, but I was also part of the small group of people that organized the meeting in 2008. So we were very excited to see this happen, but we all knew what was coming, because we decided once we approved the committee, we have to name ourselves, and we can't name ourselves 15 different things. So we had to come up with one name for the technology. We thought it would be a very long process, but it turns out it really only took a couple of hours, and this 100 or so people decided on additive manufacturing. You might ask the question, well, why did we pick 3D printing? It's a very common name. It turns out back in those days, 3D printing was the name of a process. It was developed, it was invented at MIT, and it's what we call binder jetting today. But back then, we called it 3D printing. And so the crowd really didn't want to name all of this technology after a specific one. I told people it would be, by analogy, it would be, suppose we did not know what the word automobile was. So there was no technology or nothing to describe these four-wheel vehicles that drove around. And so all the automakers get together and say, we should name this something. And the guy from Toyota stands up and says, I think we should name all of them Toyota. Even the ones made by Ford, even the ones made by Volkswagen. We'll just name them all Toyota. Well, you can imagine that's not very popular thought. But that's what people were thinking when people said, let's call everything 3D printing. We went, well, it doesn't make sense, because 3D printing is this binder jetting process. So that's what made 3D printing lose out. But additive won, and so really the reason we call additive manufacturing today is because of AST and F42's work in 2009. Okay, I want to talk. There's another entity today that I think is important to know about, and this is America Makes is what we call it today. It was called the National Network for Manufacturing and Innovation in 2011. And what it is it's an organization. It's in Pennsylvania. That basically its job is to take developments in additive manufacturing technologies and to move them into the workplace. It's to accelerate technology transfer. And it was done, the reason it was done is because it was an election year, 2011, in the United States. And you may recall we were in the middle of, the Great Recession was almost over. All the indicators had come back except for jobs. So there was basically a job crisis still going on. And there was a recommendation from the United States President's Council on Advisors for Science and Technology in the U.S. to move into additive manufacturing, because manufacturing innovations create lots of jobs, but they didn't want to do old, boring manufacturing. They wanted to do sexy new manufacturing, and additive manufacturing fit this bill. This committee in Washington included people that were involved with a workshop study that I ran, and again, it was in 2009. It was basically it was perfect for what they needed. It said basically, what do we need to do to push additive manufacturing forward in really everywhere, but particularly in the United States? Where are the obstacles? What kind of research needs to be done? And so it was a perfect fit for this group's activity. And I did it with David Rosen, who's retired from Georgia Tech now. Ming lives in Missouri at the University of Science and Technology. So anyway, Obama announced the program in March of 2011. America Makes was funded in September. It was an enormously fast process. Then Obama, in two State of the Union addresses in 2012 and 2013, mentioned it in the State of the Union address. And the impact of this is that what it did is it basically woke up the entire world to what additive manufacturing is. So you look at many countries in the world, a lot of the additive technology initiatives sort of came out of the importance of the President of the United States saying, this is a field that we're going to work in. So China invested millions and millions of yuans in additive manufacturing research after this program. And this played out other places as well, Singapore and other places as well. So anyway, if you want to know more about America Makes, there's that. But again, it's an important part of our additive culture. Okay, so let's talk about where additive is today. I have a series of plots from the Woolridge Report, which is an outstanding publication. It's produced annually, and it's a state-of-the-art of commercial additive manufacturing. So for those of us in academics, I find it valuable because I can basically go to the Woolridge Report and say, look, what I want to do research on is very important, and because of some information that's in the Woolridge Report that says that it's commercially important. So this shows the value, the market revenue from additive manufacturing worldwide. And if we jump to 2024, which is where the last data are, we see that additive manufacturing is today about a $22 billion industry. It breaks down into these various sectors here. About 10 billion in 2024 was from printing services, that's making parts. So the value of parts made was about $10 billion. The value of fabricators sold to make parts was about $6 billion. Feedstock sales about $4 billion. So that's where we are. You can see that the growth is fairly rapid since 2010. And I would note again, Obama's State of the Union addresses were right here, right? So I would certainly give him credit for at least part of this rise. This shows the Woolridge's prediction of the market value, which is in additive manufacturing in the next 10 years. We're here at 21 billion today, but in the next 8 or 9 years, 10 years, it's anticipated to almost quadruple to about $115 billion of revenue. So the health is predicted to be very strong in the next coming years. This shows what kinds of parts are being produced. And what we see is that today, about half of all the parts produced are really various types of prototypes, which is not surprising. But about a third of the parts are actually finally used in parts. So we're seeing additive manufacturing is certainly well established as a technology for producing parts that go directly into service, which is certainly where we would like to be. For prototyping, it's very important, but I think we really enjoy seeing parts going into service. And there are other technologies as well. This shows the extrapolation of the feedstock sales. Again, 4.4 billion today. In the next 10 years, it's expected to jump to 31 billion. So feedstock is going to have about an 8-fold increase over the next 10 years or so. So I think feedstock sales are going to be very healthy as well. So this is my characterization of the feedstock sales, feedstock for additive manufacturing. First is material sales, again 4.4 billion, and the annual growth rate was about 22%, which is not bad. Still, most of the material feedstocks used, again, commercially in the world, about 3/4 are still polymers. But about 20% are metals and then 2% others, which are typically composites, a little bit of ceramics. But for the polymers, about 25% are thermosets, so this is stereolithography. About half are polymer powders, almost universally laser sintering nylon, which is the most popular of the additive feedstocks. And then about 25% were the extrusion polymers. Those of you that know about those, it's no surprise. These are polylactic acid and ABS are those materials. Okay. I think I'll sort of gloss over this again. This just shows what we just said, that again, the largest fraction of feedstocks today are the polymer powders, followed by polymer filaments, which are the extrusion product. The yellow is the photopolymers, the resins, liquid resins for stereolithography, and then the metal parts are up here, all metals. This shows, I thought you might be interested in seeing how much the feedstock costs. So these are cost numbers, and basically, I would say that the mainstream value of feedstock runs anywhere from about $30 to $100 per kilogram. So it's all of these parts in here. If we focus on the metals, that includes the nickel-based alloys, the iron-based alloys, copper, cobalt, which I think is used primarily for biomed type applications, and then of course aluminum. So again, we pick all of those common additive technology material metal systems in that $30 to $100 per kilogram price range. This is polymers. I think I can gloss over this a little bit. You have it in the notes. Since we're really focusing on metals. Here's metal printer sales. So this is really, we have to be careful here. It's not the sales for last year. It's the total installs for over all time. So this assumes that nobody threw any metal fabricator away. So it shows that about a third of all the metal industrial additive manufacturing systems for metals are in the U.S. India's down here with a respectable 1% or so. And then, of course, I'm not sure who the other is. China has about a third of the metal installs as the United States. This shows the patent production. Again, you see there was an explosion in patent production in additive manufacturing starting about 2015. I'm not sure what the source of that increase is. And again, we see there was a slight drop here. I think we can credit COVID for that in 2021, 2022, 2020. And we'll see, I'm predicting that this will, in the future, will start increasing again. All right, so that's the sort of where we are, that's where we stand in the current state of the art. I want to talk about the economics a little bit. Um, so let's see, we're going till 12, 1, 12, 12:50?
Yeah.
12:50, okay, yeah, thank you. I keep track of the time. This shows that if we want, there are many reasons to use additive manufacturing. One of the prominent reasons is to save money. And so I want to talk just a little bit about where it makes sense economically to use additive manufacturing. Because what that will do for us is it will define and help us understand the application areas. Because people are applying it in places where they can save money, right? So this is the standard argument for additive manufacturing. This is a fairly common perspective of the cost to manufacture a part. So suppose I want to make N or some number of identical parts by whatever manufacturing process. I show here, I use it as an example here, a 1 kilogram nylon part. I show you see the graphic there of the cartoon. And if we want to make that using injection molding, which is arguably the most common of the polymer traditional manufacturing methods, well, the first thing I have to do is I have to create a tool set. And you see the tool set here. The tool set could cost, for argument's sake, let's say $10,000 would be a reasonable cost. I would mention just buying the blank metals, just buying the blank metal feedstock is about $3,000. So to create the shape, adds to that. So what this shows is it shows how much it would cost to make the part based on how many identical parts I want to make. So if I only want to make one part, and I spend $10,000 on a die set to make that one part, that means my one kilogram nylon part would cost me at least $10,000 because once I create the mold set, it's not good for anything else, right? So I have to eat the entire cost over my production line. So typically nobody does injection molding for one part for that reason. It's just too dang expensive. However, if I do 10,000 parts, so for example, I come over here to 10,000 parts, I'm only paying $10 for my 10-pound part. That's much more reasonable, right? And the reason why is because if I make one part, I have to burden that part with $10,000 for the tool cost plus some other stuff. But if I make 10,000 parts, I only have to burden each part with $1. And once I move or sell those 10,000 parts, I have $10,000 back to cover the cost of the mold, right? So that's the way this works. So for traditional manufacturing processes, all of them except maybe machining, we have this type of plot where the cost just skyrockets down depending on the quantity based on the tooling cost, but then it sort of levels out at some point where basically I'm making enough parts that there are other aspects of the cost structure that dominate, like the feedstock cost or the cost of the fabricator, right? So anyway, so that's what that looks like. With additive manufacturing, we don't have a tool, right? So we have just a straight line. So this shows a calculation, a typical calculation for a 1 kilogram nylon part made by additive manufacturing. And what we can see here very quickly is that if I'm making less than about 100 parts, it's cheaper for me to make it using additive than it is to make it using injection molding. However, if I go past about 100 parts, then it's cheaper to injection mold. And so we have this break-even cost associated with additive manufacturing. So this is the first of the rule of three of the considerations to make additive manufacturing economically feasible, and that is I want low production runs. That's the first number one rule. This is the reason when additive manufacturing first came into play in the 1990s and 1980s, it was used in the automotive industry for making prototypes. Because again, they only wanted to make one or two to see how it looked, and then they threw it away and moved on to something else. So it's perfect for that type of application. Okay, the second issue is this. Imagine that I want to make my part geometrically more complicated. What impact does that have on these plots? And the way the impact works is first, for additive manufacturing, as long as it's a 1 kilogram part, it doesn't move the curve at all, right? Because it doesn't matter how complicated the geometry is, the cost to produce the part, for the most part, is going to be the same. Whether I make a simple cube or a cylinder, or something with geometry figures like this face. So the additive part doesn't move. However, what happens with injection molding is that my tooling cost goes up because it's a more complicated geometry. It's harder to make the tool, and the tool will be more expensive. And so what that's going to do is it's going to drive this curve upwards. And when it does that, what we get is something that looks like this. What we see is that as this curve goes up due to the increased tool cost, my break-even point moves out to a larger number. So if I have this schematic scenario, if I increase my tool cost up here, let's say in this case it would be say from $10,000 to maybe $12,000 or $13,000 or $15,000. What happens is this curve changes, but I move my break-even point maybe out to 200 or 300 parts. And so this brings in the second of the criteria for if I want to make a part feasible, economically feasible, is I want it to have a complicated geometry. So low production runs and complicated geometries. The third of these is not so easy to demonstrate. We typically want small volumes. We want the part to be small, typically, rather than large. It has to do with the cost of the machine. I think I won't go into that in the interest of time, but just to say, basically a small part I can build very fast in additive manufacturing, whereas a large part typically takes a long time. And we want to build fast because that has an impact on the cost. So these are the three things we want to consider, and all the application space builds on these three criteria. They're all application areas where I have small production runs, complex geometries, and relatively small parts. So we start with automotive. The automotive is a big area for additive manufacturing, but it's not typically parts for automobiles because those are large production runs. But what we see are typically the types of things you see here. Certainly, we have tools and fixtures, prototype parts in additive for automotive. Yeah, automotive sales last year I looked up was about 16 million automobiles. Granted, that's spread out over a lot of different types of cars, but even if you spread it out over 100 or 200 different vehicles, that's still large production capacity. And so this is where we see it for the most part. Sports, custom autos, aftermarket customization is heavily impacted by additive manufacturing. There's one of my favorites though in automotive is if you can imagine an automotive sales where we don't sell very many cars, then suddenly it becomes attractive. I have one example. So you can rush out and buy this car that has a lot of additive manufactured parts on it. And that's in the UK. Is the Bentley is a car that has many additive manufactured parts. You can read about this. They just built 3 years ago a $3 million investment to double its additive manufacturing capacity. They built Bentley automobiles. If you notice over on the byline over there, in 2023 there were only about 13,000 built, so it's a relatively small run. The average cost of the Bentley, if you haven't checked it out lately, is $200,000 to $250,000 US. So they're a very expensive automobile, but again, produced in smaller runs so they can use additive. And so they talk about creating 15,000 parts, for their production line. And you see some of the application areas for additive manufacturing. Okay, let's rush on. Aerospace is another area where we see a lot of parts, but aerospace is completely different from automotive. You think they're the same, but they're really quite different. And the reason why is that aircraft, while they're very large objects, very expensive objects, they have literally millions of parts on a plane, but the number of planes produced, even with commercial carriers, is very small. It's a small production rate. Now, I use this example. The Boeing 747, let's look at it. It came out in 1970. The first one was produced. The production ran for about 50 years. Arguably, the Boeing 747 could be the most popular commercially produced airplane in the history of aviation. It was extremely popular, not so much these days as the future models have come out, like the 777 and the 787, the Dreamliner. But still, it was a very long production. It turns out that over the course of that 52 years, the total number of Boeing 747s produced over the entire 52-year span was 1,573 planes. So suddenly we're talking a very small production, several hundred produced per year. And so suddenly, to actually build parts and put them on the planes, it makes perfect sense, economical. And you see some of the parts here that are done primarily, I think probably the most popular parts that we see on airplanes are these ductwork things. They're non-structural, non-mission critical applications. But also, yeah, maybe you're familiar with we produced General Electric produced I forget what their turbine technology is. Maybe somebody can remember it. I can't remember off the top of my head. But it's a turbine that the LEAP engine was the LEAP engine that has fuel injectors that are made by additive manufacturing and commercial application. And again, we're just not building very many of them, so they can afford to do it economically. So it's about 30 per year. Another area, I'll rush through the rest of these. Tooling is an important area. We make one tool and use it to make a lot of parts. Medical applications are very important as well. And I'll show some example here. It's both on the right side of surgical planning models, which are very valuable, to the sort of to the middle bottom. Dental coatings is probably the most popular use of additive manufacturing in biomed. And then, of course, there are a variety of implants that have made it to practice as well. Game pieces, you can do game pieces now online, people that will produce these for you. Art is another area. Again, small parts, complicated geometries, low production runs. And art, there's a whole class of so-called digital artists in the world who do their art sitting at a computer. And they can create their art on the computer, but until there was additive manufacturing, there was no way to actually print the part. Now, because they were too complicated to use virtually any kind of manufacturing process other than maybe to hand create the part, out of clay or out of some other medium. So we see some examples here. I like the one on your far left here. That's you can tell the shape perhaps as a topological figure called a Klein bottle, because it has no internal and no internal or external surface. It's just one surface that makes the Klein bottle. A digital artist in California, Sheba Grossman, produced these parts in metal, and she created a Klein bottle opener, which I thought was kind of clever. So it actually works. I have one of these. They only cost about $50. I mean, it's relatively cheap, but we can create parts, use that. But digital art, if you really want to see where the creativity and the freedom of expression really shows up and shines, it's really with the digital artist, in my opinion. We do a pretty good job as engineers with creating designs, but the artists really do a great job. The first art show I went to for 3D printed art was in Slovenia in 2012. This shows some of the artwork that was created there. Lamp structures are very popular, I think. There's Freedom of Creation, I think, is a Belgian company that's been doing lamps for years. So we see these. I show this. This is Lionel Dean. He's a digital artist. He's standing with a model. And what's interesting about this, about the artwork in the background, is that the artwork is really not in the background. It's a headpiece that the model is wearing, like a hat. And so she shows this thing. You know, it's a wild, crazy-looking thing, but again, digital art. Jewelry is really in the same category. I show some examples of jewelry that can be made either by a conversion technology or by direct metal printing. And these are all available commercially. I use the bottom right. I use this one. This one is particularly interesting to me because if you go back about 20 years, I had a conversation with my wife, and she said, you know, basically it was around her birthday, and so I said, what would you like for your birthday? And she said, you know, she goes, you've been working in additive manufacturing for 15 or 20 years now, but I don't have anything that was additive manufactured myself. So I went, okay, I can take this hint. So what I did is I went to a website, and in this case it was Shapeways, but basically they have, you know, hundreds if not thousands of parts that are 3D printed parts that are available. And I found these earrings. They're in silver, and that was about 50, 60 bucks. Again, not real expensive. But I bought them for her, and she was very happy. So it's a great success story for me of how additive manufacturing can make society better. Architectural models have been around for a long time in 3D printing because again, they're very complicated geometries. You typically only want one, and they're generally complicated. And really, if you go back, I can remember in the very early days, in the early 1990s, there were people doing architectural models. It's not any of these, but I think it was Dion de Beer in South Africa did an African Parliament building model using an architectural model using 3D printing. Then of course prototyping, that sort of goes without saying. So I'll skip this one and we'll go from there. I want to go back and just as we close, I only have 4 or 5 slides left here. This shows sort of a chart of the standards. I want to go back to the standards. For ASTM, you know, they have the 32 standards that have been developed. ISO ASTM, the joint standards, there are 35. And then ASTM is working on 73 standards now. So they're sort of in the process of being developed to become standards. So the grand total is about 140. But you see they break down into various areas. Testing is a very large area of development because standardized test obviously has a great benefit. Design standards, there are 3 design standards. One of them is an absolute masterwork on how to design for additive manufacturing. It's a fantastic standard. I think we could use it as a textbook for how to design. Materials and processes, you see, is the largest area. Not surprising. You know, it's how to handle feedstock, how to process feedstock, post-processing, all the process stuff is in there. Environmental effects, it has standards in the works. Applications, a few of those. Then data for additive manufacturing has 3 standards. Terminology, there are 2 standards for terminology. One is 52900 I talked about, which is the dictionary. The other one is a standard on part orientation. So it's how do you describe the orientation of a part during a build, which is obviously important for communication purposes to be able to show that. So we have those as well. Here's some standards related to directed energy deposition. I wanted to show these. One is F3049 is characterizing properties of metal powders. So for the powder-based DED, it can be very important. Certainly, I think the most applicable is F3187, the standard guide for directed energy deposition processes, or for metals. It's a guide. It's basically sort of a how-to, things you should think about it if you're doing directed energy deposition. Then of course I list 52900 the dictionary. 52921 is the coordinate system. That's the other one. And then we have at the bottom a standard guide for issues associated to requirements for purchase additive manufacturing parts. Okay, so this one, there's some general issues here. Some of them I think maybe doesn't apply directly to directed energy deposition. For example, the first one I think really it looks like it's a powder bed attack, so we'll ignore that one. But 52920 again is a joint standard between ISO and ACM on qualification principles, requirements for industrial additive manufacturing processes, and production sites. So again, it's very important for commercial production. The next one is qualification, installation, operation, and performance for powder bed fusion. Again, maybe not so applicable, but a lot of the considerations would cross into metal D and E. And then, of course, we have qualification of coordination personnel for metals applications. This would again cross into D and E. So my almost last slide is on the historical perspective. This is there was a group that did a road mapping study, a commercial additive manufacturer. They called it rapid prototyping back in those days, but what we call additive today, they call rapid prototyping in 1998. But what they did is they said basically, where's this technology going? It was a group of people, primarily industrial people, was led by Terry Wohlers from the U.S., and it was sponsored by the National Center for Manufacturing Sciences. And it was really a nice prophetic kind of piece to describe the where we're going with this technology. And they missed that they were incorrect on the details, but they were correct with the big picture. And that's what I want to show you, is that they were correct with the big picture. So what they say is they basically said, here we are in 1998, and here's what the future looks like going all the way to 2010. What they said is there was going to be a separation of the technologies into three groups, and they were correct. We have these three groups today. They said the first one is going to be what they call design verification system. What we would call it today would be the low-cost printers. So it's like the extrusion machines and those types of machines that are very cheap, very readily available for producing low-quality parts. Inexpensive, disposable materials. Right? That's that. But then at the other end are the direct manufacturing systems, and while they were maybe not right on the applications, they were correct that we were going to find some very expensive machines that can produce service parts that have the correct properties to go into service applications. And that's this one. So we have these two branches today. The third branch in the middle, the bridge technology systems, I call these conversion technologies. And you can see that they, in their definitions, they list as examples castings, laminates, wax molds, and resins. So these are basically where I use additive manufacturing to create the shape, but not in the right material. And then what I do is I take that part and I somehow convert the material from whatever it is into the material that I want. And so, for example, the classic case would be using additive manufacturing to create a wax pattern, and then to use that wax pattern to form a mold cavity, like, for example, a lost wax type technology, and then to create a metal part. So this becomes a way to get to that level. And so the conversion technologies, those are also very applicable today. Okay, so let me, I'm ready, I think, to move into a summary. And I think we'll have some opportunities for maybe for some discussion, or I can talk about some other things too, as we see. But anyway, let's look at where we're at here. I think additive manufacturing, depending on how you define it, really dates back at least 150 years. One could argue maybe, that, depending on your definition, I guess it could go back to antiquity. But generally, the idea of using layered processing to create a small part, would be at least 150 years. Again, we break it into three categories: the prehistory, the precursors, and the modern technologies. It's rapidly growing, and the technology over many years has grown at about 25% per year in terms of the application space of the usage. Powdered polymers, the most popular feedstock. Then it's followed equally by the photopolymers for stereolithography, polymer filaments for the material extrusion, and then wire metal powder it's predominantly used for directed energy deposition and powder bed fusion. There are a few companies that are using more indirect approaches, like Desktop Metal and X1. They're doing, I guess, hydrojetting with metals. Mark Forge is doing extrusion with metals, but primarily the big dogs are directed energy deposition and powder bed fusion. Then, of course, additive manufacturing. It's economically feasible, low runs, small parts, complicated geometries. This is where we really want to focus. And within directed energy deposition, this is really a primary application space. So it fits very well for many applications. So let me just show you here. This is the last slide I have. I show you where Texas is in case you don't know, and where Austin is. This is the campus at the University of Texas at Austin. The tower building is the main visual element of the campus, as well as the big, American football stadium, which of course is very important too. But I show on the map of the United States the little red bullet at the bottom there shows within the state of Texas where Austin is. Austin is the capital city of the state of Texas. I guess someone like maybe Hyderabad is for our state here. But and so one can go. Actually, I don't show it, but if you go our state capitol building, if you go from here, if you go right down this road, about right here is where the state capitol is, where all the seat of the government. That's where that is. So with that, I think what I will do is we have maybe about 20, 25 minutes. We can, if there are questions or something you want to talk about, I'll give you an opportunity to do that. But then I think what I would like to do is if there are none, then I can tell you some additive stories about the technology, and I think we can talk about those as well. So with that, maybe I can open it up if people have questions. So.
And various applications and its experience where you have started additive manufacturing. Participants, if you have any queries regarding this initial things or anything about additive manufacturing, we'll be happy to answer. Yeah, anybody having any queries?
Telling stories.
Yeah, please. Yeah, of course. He wants to have some queries.
Yeah.
Is direct fiber manufacturing, direct fiber energy deposition is also a part of energy deposition?
Yes, yeah. And the idea I need to preface answering your question with a comment first. Just so everyone knows, because we're going to be dealing with this really all week. With the I'll get to your question. We're going to be doing this all week. I'm in the process of losing my hearing, so people need to know this. And so it's very difficult in certain cases for me to really understand very well. So what I do, I'm pulling out my cell phone, and we're going to see how this works. I actually have a translator that helps with the with me understanding the questions. So we'll try this, and I'll try and understand these. But you know, my this ear is completely deaf. This one's about half gone. So I have hearing aids that are supposed to help, but they're not perfect. So you'll have to be patient with me when we have the interactions through this week. And I don't know if if we can't make it work, otherwise maybe even have to write questions, or you can maybe interpret for us.
Definitely.
Okay. So anyway, with that out of the way, yeah. So please.
Is direct fiber deposition is also the part of direct energy deposition?
Right. Yeah.
How it
Direct
is
fiber, the fabrication of fibers.
Yes.
Yeah, it's a good question. Yeah, I typically don't really consider the fabrication of fibers to fall within the realm of additive manufacturing technologies. I think of now there are additive manufacturing technologies that produce continuous fiber parts, and that of course would fall. But I guess I don't really see the part specific geometries that I typically associate with additive manufacturing. So that's my run on it. Yeah. I would mention, by the way, that since we have time, there are a number of processes that sort of fit the definition of additive, but arguably maybe they fit or maybe they don't. Some fit, but they don't. Well, we don't think of them this way. For example, what is it? Micro electronic machines, MEMS technology, which is sort of a silicon-based lithography. That one can argue that that's additive manufacturing, but those people never come to our meetings, and we never go to theirs. They do their own thing, right? The other one is there was an additive manufacturing process that involves sort of subtracting material, and it's like, well, that really doesn't fit, but yet we include it in our technologies. It's one where I guess basically a part is built up with very simple geometry, but then machined. We'll talk about hybrid, later. But is it really additive or is it something that's, who knows? But there are a number of these, and again, we just, today, the field is sort of self-defined what belongs and doesn't. But and that's really what we go with in terms of is it additive or is it not? So, anyway, so anything else?
Yeah.
Yes. Sure.
If the laser direct energy deposition can be applied for machining cutting tools?
Let's see what I have here.
It's asking laser energy deposition can be applied for manufacturing some kind of cutting tools.
Oh, for manufacturing cutting tools.
Yeah.
Yeah, use additive.
Yeah.
Use additive to create cutting tools.
Yes.
Yeah, it's a good question. Tooling, it certainly fits the area, the application space. We talked about tooling. The tools I showed were primarily forming tools, but cutting tools reasonably could be made if we can get the right feedstock, right? And that's the trick, because these are very high performance feedstocks. They're very high quality tool steels or carbide materials typically, and I guess there's some ceramic cutting tools as well. But if we can get the feedstock into the right, if we get the right proper feedstock, these technologies, including DED, should be able to produce cutting tools. I see no reason why they couldn't. Yeah, absolutely.
Thank you. Any other queries? Yeah, so I have one query.
Sure.
Any real-time component are they using in dynamic aspects of this manufactured parts? There are any dynamic applications of these IT parts currently?
Dynamic? Dynamic is a...
Yes.
Yeah, the application space, anything exciting coming in? Yeah, thank you. I understand that. Yeah, I'll talk about, I don't want to steal my thunder, but I think the last lecture talks
Yeah.
about where we're headed, what the
Future.
future looks like. So
Okay.
I'll save some of that, but for me, I think I think what we're on the forefront of, really in many areas, but particularly in additive manufacturing, is what the impact of artificial intelligence will be. And there are, if I could do an advertisement, I'm not directly associated with the SFF conference anymore, but the SFF conference this year, it's in August in Austin, where it always has been. But the morning plenary session will be on artificial intelligence in additive manufacturing. So we have 4 or 5 talks from leading experts from around the world on how we can use basically machine learning and artificial intelligence principles to impact in a positive way additive manufacturing. Just the two examples that I find interesting, I think maybe I talk about them at the end of the week, but the 2 examples, one is really a sort of an engineering, not too exciting but very important application, is parameter optimization. Because the way we do parameter optimization today largely is we have 3 or 4, we pick 3 or 4 important topics. So for DED, it might be the laser power, the scan speed, and the scan spacing, maybe the layer thickness. You know, we stop there, right? However, there are maybe 50 or 100 parameters that we can set on a given machine in order to, to try and optimize parts. We stop there because that's plenty for us to deal with. Well, consider artificial intelligence. We can come in, artificial intelligence can look at all 50 or 100 process parameters and come up with, let's say I want to maximize the mechanical properties, or I want to make the smoothest surface finish, or whatever the requirement is. We can give it the requirement and say, optimize all 100 of these so we get the best part. I think that's a good engineering application for the technology. People are working on doing this around the world. The other area is a little more exciting, I think, and that is for file generation to print. So, for example, today, I'm by no means an expert on commercial additive artificial intelligence, but I watch my 8 and 10-year-old granddaughters play with it, and it's fascinating to see what they can do. Just by talking to ChatGPT and saying, create this for us, and what comes back is amazing stuff. Well, what we can do today with AI is, I could go to AI and instruct it verbally, but create a drawing of a flower that looks like a rose, but that was drawn by a 4-year-old, right? And it can generate these things, right? And to do a reasonable job. Well, imagine in the not too near future coming to AI and saying, generate me an STL file of a chair that's 20 centimeters tall that is shaped like a banana. Right? And AI will, in the same way, very quickly generate the STL file. And then of course we can iterate the way you always do it. If it doesn't look right, add some grapes to the chair. I mean, you can do these kinds of things. Now, this is sort of a trivial example, but hopefully it kind of illustrates where we can go with AI in terms of being able to facilitate the design of parts to be printed that are totally customized. And I think what it will do is it sort of fills a gap that doesn't exist now. Because what we have is basically I have 2 options today. And one is I can basically learn a CAD program and do it myself. I can hire somebody that already knows how to do it and pay them a lot of money to create my banana chair. Or I can perhaps go online and sort of hope and pray that there's a banana chair out there that I can modify and print myself, right? None of those are perhaps very attractive, and I think it becomes a real real niche that we can fill with artificial intelligence to be able to do this kind of file generation. So I think that's probably where we're going to be in 10 years. I think this is really, for me, the exciting area.
Okay.
So,
Do you think that this is going to be fully commercialized in the industries?
yeah, I think so. The first use of the term 3D printing was in a trade journal in, I think, 1988. And it was coined by Terry Wohlers. He wrote the article. He had seen a year earlier, he had seen the first SLA machine that Chuck Hall put together in 1987. He saw it at a trade show, but there was no name for the machine, so he coined the term 3D printing. But then that was sort of forgotten. So then you jump forward about 4 years to Ellie Sachs at MIT in the United States, who developed what we today call binder jetting. He invented that technology, and he wanted to have a term to define what this was. And so his father was a commercial printer, a 2D printer, in the Boston area. And so Ellie had this idea, well, why don't we call it 3D printing? But he sort of played this term out with several of his students and some faculty members to get input on whether it was a good idea or not. And the general consensus was it's not a good use of the term. It's not a good term to describe your process, and you shouldn't use it. But Ellie decided, like many faculty under certain circumstances, he decided to ignore the crowd. He says, we're going to call it this anyway. And so his technology, his patents that came out again in the early 1990s were all called 3D printing. And that's what really took over, really with the press and with the do-it-yourselfers. They really liked that term. And so the question, then the question becomes, well, 3D printing or additive manufacturing, people ask me, which one's going to win in the long run? Terry Wohlers and I had this conversation about 15 years ago. And Terry said, 3D printing is going to take over, and additive manufacturing will disappear. I bet him a beer that he was wrong, and we still haven't collected yet because we're still waiting to see what happens. But what I feel is I think that both terms are going to coexist together. And so some places we'll call it 3D printing, some places we'll call it additive manufacturing. And the reason I think that is because there are a number of manufacturing processes that have multiple names, right? So we think of, you think of investment casting and lost wax casting, right? Or you think of shielded metal arc welding or stick welding. Or you think of gas metal arc welding and MIG welding, right? All the same process, but depending on who you talk to, you get different terminologies through it. And I think that additive and 3D printing are going to continue to be this way. I go places and see, typically the academics tend to gravitate towards additive manufacturing, but not universally. I mean, perhaps the largest university effort in the world in additive manufacturing is at Nanyang Technological University in Singapore. They have perhaps maybe $40 million US of equipment. They have their own building. They have a large academic program in additive manufacturing, except on all the doors it's 3D printing. So they don't use additive, they use 3D printing. So, so who knows where it will go. But anyway, so the academics use it. Historically, the politicians use 3D printing, but Obama used additive manufacturing. The press, typically 3D printing. If you see a news story on TV about additive, they usually will say 3D printing, right? So it seems to be more common term. If I could close with just one side story on additive manufacturing, it's a sad story because it was a failure of the technology, of the terminology. So you flash back with me to 2009 in January. The ASTM committee met. We finally decided we were going to call this technology additive manufacturing. So that was great. That was wonderful. So you fast forward now about 5 or 6 months to the summer of 2009. I was at a National Science Foundation grantees conference. So it's all the people who had NSF grants. So it's a large group. We met in Hawaii, in Honolulu, and I ran into an old college buddy. He was at Case Western Reserve in the United States. And so we were, one of the social events, we were just getting caught up, what are you doing? What are you up to these days? And so when he asked me the question, I thought, here's the perfect example to demonstrate how intuitively, conceivably easy and simple and definitive the term additive manufacturing is. So without any description at all, I said, oh, I'm doing additive manufacturing. And his comment, he came back, so he said, oh, so you're talking about the manufacture of titanium oxide as a brightener for paint, or some other additive, right? He was thinking that I was making additives as opposed to using additive processing. So it was a complete misinterpretation of what the field is. And so, so he was talking about, oh, you're doing fillers and polymers, and manufacturing, working with sawdust or whatever. And I mean, oh, it's a complete failure. That was the only time I think that that we missed the mark with additive. I think it's pretty intuitive now that we know what the technology is. So with that, I think we're probably pretty close, I think, to being done. So.